Okay, in the spirit of Ed Kern's noun quote, I'm going to tell you what the research community is smoking these days. My name is Nick Feamster. I'm a graduate student at MIT. I'm going to tell you about some work that I did with Jennifer Rexford and Jay Borkenhagen from AT&T. This talk is essentially about good BGP traffic engineering practices. I'm going to talk mostly about the types of BGP import policy changes that are good and some which are not good. So the contributions of this work are really twofold. The first is really what I'm going to talk about today. So in this work we propose a set of BGP traffic engineering practices that scale well, that allow operators to make predictable changes to traffic flows, and that do so even in the presence of neighboring ASs which may be doing things that you can't always predict. So the second contribution is a tool for predicting how egress routes change in response to these BGP import policy changes using an offline algorithm. And I can refer you to some of that work if you're interested. Okay, so if you don't know why interdomain traffic engineering might be interesting, there's going to be a panel on it tomorrow morning, but I'll give you a little primer now. There are several companies, obviously, that are interested in doing this these days. But some of the main reasons you might be interested in doing this are if you have congestion on some of your edge links, you may wish to shift traffic around to alleviate some of this congestion. As provisioning changes on these links, you may want to direct traffic, towards links where provisioning has increased, and you may wish to alter the end-to-end path to various prefixes to achieve better end-to-end performance. So in sloshing this traffic around, there are really two main options. You could shift traffic among the links to a single AS, or you could shift traffic, among all your links, maybe to a different AS. So I'll talk about good ways to do both of these. So the first thing to realize when you're sloshing this traffic around is you really have to pay attention to where you're sloshing your traffic to, because you don't want to violate commercial constraints. Certainly you don't want to take traffic off one of your peering links because it's congested and then end up sending it through one of your customers or something like this. So we got to pay attention to this carefully. So as a general overview, we're trying to change our outbound traffic patterns by tweaking BGP import policies. Well, one alternative might be to just get rid of BGP, but many of you probably wouldn't be very happy if we shut the internet off one day and brought it up the next, something else. And we don't have any better ideas with what to bring it up with anyway, so let's just stick with BGP and see what we can do. So what types of BGP import policy changes are considered good? Well, there's several criterion by which you can consider a route or an import policy change to be good or bad. So good changes should really impose a minimal amount of management overhead and also a minimal amount of traffic as far as sending out new BGP updates. The changes we make should result in predictable changes in the traffic flows, and the changes we make should try to minimize as much as possible our neighbors' reactions to our own changes. So really what we're interested in is trying to model what's coming out on our egress links as far as traffic loads, given 5 different inputs, several of which operators have little to no control over. Operators don't have much control over routing advertisements that neighbors are giving to them at any given time for a prefix, not much control over the network topology, or there's limited control as to the quantity of the balance of traffic that you're getting on the inbound traffic links. So there are a few things that we can play with in response to this to try to shift the traffic around on these links within our network and on the outbound edge links. One is that we can tweak the IGP configuration within the network, but when we're shifting traffic on these outbound links, it's generally easier to do this with BGP import policies. Well, how can we even hope to model this or predict what's going to come out of this black box when a lot of the inputs we're dealing with are rather unpredictable? And even what's inside this box can be unpredictable itself. For example, if router's not configured correctly, BGP decision process may not be deterministic itself. So how can we make some of these inputs and the box itself more predictable so we can hope to model what's coming out as far as traffic loads? So there's some further difficulties that we also have to deal with. The first is difficulties with the protocol itself. There's the message advertisements don't include any sort of metric as far as performance is concerned. So traffic engineering is essentially manual. The second set of difficulties that we're dealing with are related to the configuration itself. So essentially what we're trying to do is influence the router's selection for best route to a prefix, given only our handle on these import policies. So we're trying to set attributes on these routing advertisements that we hear, and in such a way where we only have an indirect capability of influencing which route a particular router picks for a particular prefix. The third set of limitations that we're dealing with are limitations with the BGP decision process itself. Namely, splitting traffic in many instances can be difficult, and interacting with the IGPs also introduces a fair amount of complexity. And there are also these commercial relationship constraints, which I alluded to earlier. So I posed the question before of how to actually make some of these inputs more predictable. Well, the first thing we want to do is make sure our routers are configured correctly so that, given a static snapshot, essentially, of our configuration and of the set of routing updates we're hearing, we can predict what type of routes are going to be selected. To do this, we need to make the BGP decision process independent of the ordering of message arrivals. So BGP deterministic med will allow the current best route advertisement to be compared with all the other route advertisements for that prefix, and therefore the ordering of these arrivals does not affect which route the router picks. The second thing we want to do is not use tie-breaking based on the oldest route that we've heard for a particular prefix, but rather use the router ID. Now, the router ID itself can change if routers reboot or things like this, but we're really interested in, given that we have a snapshot at a particular time, let's not have to simulate, the order of message arrivals. Let's assume a particular state and see what we can predict as far as best routes. So when we're playing with this box and tweaking our inputs and trying to see where traffic is sloshing around to, we're also concerned with minimizing the overhead. So to achieve traffic engineering goals, we'd also like to minimize the frequency of the changes that we're making in order to reduce the number of BGP messages that we have to send, as well as operator headaches. And we also recommend enabling soft reconfiguration or route refresh, such that every time a configuration change is made, the session doesn't have to go through a hard reset. So given that we've sort of laid these basic ground rules, the rest of the talk basically focuses on how we're going to adapt these BGP import policies in nice ways such that we can predict what's going to come out of this box as far as how much traffic is coming out on each of our egress links. So really we propose sort of three main areas in which we want to focus. One is that it's important to consider the scale of the problem. We've got as many as 100,000 prefixes and several advertisements for each one, and we don't want to have to set independent policies for each one to try to shift traffic on a prefix by prefix basis. This would lead to particularly long unreadable configurations and will likely be unstable because it's hard to predict how much traffic is going to be destined for any one particular prefix at any given time. So the second thing we're interested in doing is achieving some amount of predictability. And I've alluded to this a little bit, but there's a lot of things that can happen when you make an import policy change, particularly if your neighbors see the effects of that change. This can affect inbound traffic patterns, et cetera. So we'd like to limit the types of changes that we can make such that when we do make a change, we can predict where our traffic is going to flow. So the third thing is we don't have much control over which routes our neighbors are advertising to us. Some of the attributes we don't have much control over, and we don't have much control over how much traffic our neighbors are sending us on which links. So, so what can we do about that? So we basically look at these three problems in the context of the data we have available from the AT&T backbone and see what types of changes will be better than others under these three guidelines. So we look at routing table data, which give us an idea of the advertisements we're likely to see for a particular prefix. We use aggregated net flow data to figure out how much traffic is going to each particular prefix over these outbound links. And we look at the configuration files to see what types of policies we're applying to each of these advertisements. Okay, well, not everyone works for AT&T. So what can you do if you don't have this type of information available to you? Well, you could use an iBGP monitor to get some idea of the route advertisements that are seen for a particular prefix. Or some vendors support sending all the advertisements heard for a particular prefix to an iBGP monitor. Instead of using NetFlow, you could use packet monitoring or some other technique. And the analysis that we're presenting does apply, even if you only have limited access to this type of data. So the first problem I alluded to was that we've got a large number of prefixes. We'd rather not have to set an import policy on every one and keep changing these as traffic patterns change. So let's look at the traffic characteristics for these prefixes and see which prefixes are carrying the majority of the traffic and only set import policies for these prefixes or these groups of prefixes. So that's what I've shown here in this graph. On the y-axis, we have the cumulative fraction of traffic that is being carried for a particular prefix in blue or origin AS in red. And then on the x-axis, we have the cumulative fraction of all origin ASs or prefixes. Okay, so at 0.1, 0.7 roughly, you can see that 10% of prefixes are responsible for terminating about 70% of the traffic. If you group these prefixes according to the origin AS that advertises them, 10% of those origin ASs terminate about just over 80% of the traffic. So 10% of the origin AS is about 1,200 origin ASs or so. This is a much more manageable number than dealing with 100,000 prefixes. Okay, so the second problem we're interested in dealing with is making predictable changes to the import policy. Okay, so the first problem is that the traffic that our neighbors are offering us on our inbound links is changing over time. So if I'm changing import policies based on these prefix advertisements, the obvious solution is to change our policies for the prefixes which carry a roughly predictable amount of traffic from week to week. So which prefixes are those? Which ones carry a relatively predictable amount of traffic? So it turns out if we look at the prefixes which carry the majority of the traffic, those tend to be more stable than the prefixes which carry less traffic. So, for example, the top 1% of the origin. I'm sorry, I said prefixes, but I meant origin ASs. So, if we look at the top 1% of these origin ASs that terminate traffic, as far as how much traffic they terminate, these only experience a 10% change in the amount of traffic that they're terminating from week to week. And most of the origin ASs that are responsible for more than 10% of all outbound traffic over these links don't change by more than a factor of 2. So focusing your import policy changes on only these sets of prefixes may be likely to give you more predictable output as far as how much traffic you're carrying on each of these links. Okay, so the next sort of problem we deal with when we look at predictability is that when we make some import policy change that affects a router's choice for best route, that change may be visible to our downstream neighbors, and that change may cause them to, in turn, change their mind on where they're sending their traffic. So in this diagram, if I've made some change that changes the path for a best route from ASB and that's now using ASA, my downstream neighbor may decide, oh, I'm not going to send traffic to my network at all. This is going to wreak havoc as far as generating predictable inbound traffic matrix. So in order to alleviate this kind of problem, we'd like to make import policy changes that shift traffic either to the same AS, or if we need to shift to a different AS, at least shift to a path that uses the same path length, so this is less likely to change your downstream neighbor's choice for a best route. Okay, so what this graph is showing is it's the cumulative fraction of traffic and prefixes for so for a given basically we can see from the graph that about 70% of the prefixes have only one distinct next hop AS for the among the paths they hear for shortest path advertisement. So this is nice because this means that we can play games with our import policies, and as long as we shift among paths that are all the length of the shortest path of all the routes we hear, we don't have to worry that our traffic is going to slosh to a different next hop AS. So the next problem we have to deal with is that operators typically want to shift traffic aggregates on some finer granularity than on a per AS basis, but on a more coarse granularity than per path. So, for example, they'll pick out a chunk of traffic like a UNet Sprint path or something like this and shift all of that traffic away from a particular link. Okay, so the problem with doing this naively is that if you pick a specific 2-hop path and somebody 2 hops down from you decides to change their advertisement, then the policy that you've just set has become invalidated or not applicable, rather. So what we want to do is use regular expressions to try to figure out or try to alleviate this problem of this flapping downstream. So the main thing to be careful of when we do this sort of thing is that a 701 slash 701 N hop is not the same as a 701 M hop. There are different types of networks, and the amount of traffic that's terminated over networks of different paths can vary. So you could probably, if you're feeling astute, you could probably figure out who each of these ASs are. But the point of this graph basically shows how much traffic is terminated to each of these ASs over various path lengths. So, for example, ASC terminates 100% of its traffic over 1-hop paths, whereas someone like ASA terminates only 20% of its traffic over 1-hop paths, and another 25% or another 30% over 2-hop paths. So if I want to shift 2-hop paths to some particular AS, I have to be careful about what some particular AS is, because the change I make could have vastly different impact depending on which AS that is. Okay, so the last challenge we're trying to address is that we don't have a lot of control over advertisements that our neighbors send us. And the AS path length step in the decision process comes fairly early, and by default it's not something we have much control over. Further, in many cases it's not clear what the difference is between a 2-hop path and a 3-hop path. So in particular, when we're trying to shift traffic to achieve various traffic engineering goals, using sort of a strict AS path length rule ends up restricting our flexibility, because we're ruling out paths that we may want to be able to use to offload our traffic to or from. So if you want to do this sort of thing, we recommend turning off the AS path length step and using a more coarse definition, or using sort of a more coarse-grained metric to apply the AS path length step. Maybe say, 2 or 3 hop paths are roughly equivalent, but definitely prefer those over a 5-hop path. Okay, so what we're showing here is how many prefixes here are advertisements with paths of more than one distinct length. So we see that about a little more than 35% of all the traffic and a little more than 35% of all prefixes hear advertisements for more than one distinct length. So this, from a traffic engineering mindset, this should raise some flags, because for those 35% of prefixes that we want to maybe slosh around, we may be restricting the choices that we have as far as our egress links by ruling out a particular 3-hop path because there's a 2-hop path that looks better by the BGP decision process. This often, a lot of these multiple length paths do come about because of prepending, and that's actually what I want to talk about next. So the issue with prepending is there are a lot of people that sort of prepend vigorously. Prepending 12 or 14 times it actually happens, and it's unclear what the difference is between someone who's prepended a route 7 times or someone who's prepended a route 8 times. You know, as far as doing traffic engineering, if we want to keep our options open, we don't necessarily want to prefer a 7-hop path over an 8-hop path. Why don't we just consider those to be equally good? I mean, we definitely want to prefer a 1 or 2-hop path over a 7-hop path, but using such a coarse-grained metric can restrict operators' flexibility. So the last thing that we're really concerned about is things that our neighbor ASs may do to try to play games with us and restrict our flexibility in choosing outbound routes. Games like filtering on some peering points and not others. You know, advertising a next hop IP address that's not of the session itself, but you know, somewhere across your backbone. We didn't see this happening that much, but if you do, it may be causing you some headaches. So definitely something to look out for. So pay attention. Pay attention to your advertisements, at least, if you haven't been paying attention to me. Okay. So in conclusion, we're pretty much stuck with BGP, so we need to figure out how to do interdomain traffic engineering with it, and that's basically what I've been talking about today. What are good types of import policy changes that result in you know, good scaling properties, that result in predictable changes in traffic flow, and that allow us to do things despite the fact that our neighbors may be sending us things that we don't want to hear or misbehaving in various ways. As I mentioned, there's also a tool we're developing to do this sort of prediction that I described offline. I'll refer you to the paper that's also linked from the Nanog website. Just one last thing. The research community is also smoking a few other things, and this is a shameless advertisement. Some of the work I'm doing as a graduate student at MIT involves answering some questions like observing correlations between BGP advertisements and end-to-end path failures. But to observe these correlations, we need to have places to observe them from. So that's where you come in. Randy Bush has been kind enough to help us out with giving us a point of presence in his network, as well as an iBGP monitor. And we'd appreciate it if you would do the same for us. Thank you.
There's time for some questions. If folks want to step to the microphone. Since you mentioned the analogy for smoking stuff, who's funding your habit?
It's actually DARPA. Yeah. Yeah. Thanks to the government. Was anyone paying attention?
Avi, you're waving. You have a question? No. Ah.
Okay, well that's good. You all have to go out and apply this now, since there's no argument.
Great, thanks a lot.
Thanks.